Good evening, everyone, and a very warm welcome to you. Warm being the ultimate word this evening. Up in Inverness here, I'm just looking, we're minus 4.1 degrees. I still have about 30 millimeters of snow on the ground, so it's still very chilly out there, but it's rather pleasant all the same. Nice to see the snow. My name is Gary Johnston. I'm the chair of the Armet's Scottish Centre Committee and Vice President for Scotland of Armet. You'll see that there's a few slides up there, and what I would like to do is encourage you to join Armet. It's a very worthwhile organisation, and they certainly provide a lot of information. So if you have an interest at all in meteorology or the weather at all, please just look at the Armet's website, armets.org. Okay, now, just before we move on, there are just a couple of quick announcements. The quality of sound should be good tonight, but if you find your sound or picture is not as good or you expect, I would encourage you to restart your browser. Chrome is the software vendor for the preferred browser we're using for the talk tonight. Okay, before I introduce our speaker for tonight, I would like to just say a personal thanks to Dr. Vicky Ingram, who is the past chair of the Armet's Scottish Centre and Vice President Scotland. She was in post before me, and she's been incredibly helpful. Vicky is standing down from the committee, and the committee would like to thank her very much for all her leadership and her time serving on the committee. It has been very worthwhile, and she's been incredibly helpful and knowledgeable. This, of course, will leave a vacancy on our committee, so if anyone else would like to join the committee at all, please get in touch with Richard, our secretary. You'll find the details on the website, and we'll be glad to hear from you. You don't have to be a meteorologist or an academic. I myself, I'm just an amateur. And there are still a lot of amateurs who are members of the society, so we are more than welcome to participate. Our talk will be recorded and will be available on YouTube in the next few days, once our speaker has granted his release permission for the talk. You will notice that we're using Zoom, and at the bottom of Zoom you will see a notice board. It is called chat. Please feel free to put a question into the chat, and I'm sure that our speaker will be glad to answer any questions at the end of the talk tonight. If there's a specific slide that you would like to raise a question on, could I ask you just to note the name of the slide and number of the slide, and we will try and refer back to that when your question is asked. So just, I would like to introduce tonight our speaker, Professor Simon Ted. Professor Ted Simon is well known to us at the Scottish Centre because he's a member of our committee, and we're very grateful for his talk tonight, which is the impact of an extreme cloudburst on Edinburgh Castle and how important were human influences in it. So a fascinating talk. So in saying that, I will hand over to Simon, and who will lead you through his slides. And as I said, please note any questions that you wish in the chat, and I'm sure Simon will be happy afterwards. So over to you, Simon.
Thanks, Gary, for the introduction. And yes, I'm not sure I'm that well known. I've only been on the committee, I think, since October. So this is some research. This is talking about some research that was jointly funded by Historic Environment Scotland and the National Centre for Resilience which is trying to better understand how climate change might impact our sort of built heritage or our cultural heritage. And it's a collaboration. So Kate Donovan was actually the PI on the project. We had a joint master's student who in many ways started the whole ball rolling, but we finished it because he got a job. And then Younghua Cha and Gina Maria Geffers did the bulk of the work, and Ed Hawkins contributed something very useful about how we might be able to relate what we're seeing to climate change. The idea behind the talk is that is developed from my interest in what I might call extreme weather attribution. So when an extreme event happens and has impact on society, some of us like to know how important were human activities, human-caused climate change in changing the risk of that. So it's a sort of risk and probabilistic thing. But the other important part of this, which is what Kate and Younghua led on, is the impact. Now, I'm going to only, if I felt I only had about 40 to 45 minutes, so I'm going to be fairly general. I probably get into most detail over the things I'm most comfortable with, which is the sort of changing risk estimation. So with the exception of Ed, we're all at the University of Edinburgh. Ed Hawkins is a professor at University of Reading. So part of this, or the part of the motivation for this, is in Scotland, we have a lot of cultural heritage, and Edinburgh Castle is perhaps the prime example of that. We're also worried about urban resilience as climate change causes changes in extreme rain. And we expect rainfall to get more extreme in response to a warmer climate. And the Climate Change Committee has had a good kicking at the Scottish Government and also at the UK Government about the adaptation to climate change is not keeping pace with rapidly changing risks. And one of the things that drove this was there was a extreme rainfall event on July the 4th, 2021 in Edinburgh. I happened to be away when that was on. I was enjoying myself in Shetland on my birthday. But a colleague from the Royal Botanic Gardens got in touch with me and said, we've just had, quite a bit of damage, what's going on? So we essentially put the proposal together. From the point of view of Scottish National Heritage, they have no, and in fact, many places have no systematic way of recording post-event damage and lost information. And if we're going to think rationally about climate change and adaptation, we do need to know the cost or the impact of these extreme events. So that's what we're trying to do here. So let me, I actually put this talk together first for colleagues at the Met Office. For some of you, anyone who's based in Edinburgh, this is probably stuff you know. But here's a picture of Edinburgh Castle looking from the north of it. And a main point I want you to take away, this is a high point. This dominates the landscape. That, of course, is why the city of Edinburgh grew here. It's a naturally defendable fortress. So this is not a site that's sensitive to rivers flooding it. It's above rivers. And its issue is probably getting water. And then drilling into the castle, the biggest impact took place in the buildings around Crown Square, which are actually, I had a lovely tour around the castle just before Christmas when they were doing their light show, which is actually the highest point of the castle. And what we're going to see is that's the place that had the most impact. So this is essentially a response to extreme rainfall, not mediated by rivers or watercourses flooding. So that's the sort of orientation. And then drawing out a bit more, again, I suspect any of you from Edinburgh or Eastern Scotland don't need to see this. What this is showing is essentially the local authority boundaries as a way of orientating ourselves. Here's Edinburgh, that purple dot is centered in Edinburgh Castle. Each of these darker areas is capturing the urban landscapes of places that land map would think is urban. Over here, critically, is a radar station at Munduff Hill, and we'll see that radar station is quite important to the analysis we do. The other thing that I think is worth noting is quite how the coastal plain around the Firth of Forth is actually quite narrow, and the mountains or the hills around Scotland reach 400 meters within a few tens of kilometers of the coast. And then, for any of you who are joining from outside Scotland, here is where Edinburgh is in Great Britain and Ireland. So bear that in mind. We've got the sort of hills around, quite a narrow plain between the Firth of Forth and the hills, and then these red lines are the various boundaries. And here's the radar network station, which I'm going to use. So what happened on the day? So this is from the 1 kilometer, 5-minute radar rainfall data over 3 hours. The third plot is smaller because I'm trying to show both the rainfall in a logarithmic scale. So this goes from 5 through to 200 millimeters. It's 5, 10, 20, 30, 40, 50, 100, 200 millimeters per hour. And here's the topography in a colored scale. So we see, here's Edinburgh, we see at 3 o'clock essentially a convergence line. If you look at the edition of weather that has the charts for this day, you can see there was a convergence line shown, and then it sort of moves across over the next 24 hours. So here it is at 3 o'clock with some spikes of heavy rainfall in it. 1600, and this is all summertime, we get a heavy burst of rain over the city itself. And then by 1700, it's basically cleared away with perhaps some heavy rain at Edinburgh. So this is a small scale, and I'll show you in more detail how small scale event that did not last very long over Edinburgh. Here is some data from the radar over a really small point from 1500 on the 4th of July through to 1900. This is again showing 5-minute radar rainfall at 2 points. Here's the castle, here's the Botanic Gardens to the north. The Botanic Gardens has a gauge. And what we see is that the sort of peak of this event is very narrow. So you see essentially we hit some very high hourly rates in our 5 minutes, up to 140 millimeters. But the rain itself is basically over in less than an hour. And in fact, depending on where you want to draw the line, is really a 15-minute event. Here shows on the day, the 4th of July, 2021, scales 5 kilometers. So we've zoomed in over Edinburgh. This shows the maximum rainfall in any 15-minute period on that day. And the point I want you to take away from this is that this is a very narrow band where we have very extreme rain. And in many ways, it was a bit unlucky the castle got hit, or the Botanic Gardens got hit by that. Of size of 1 to 5 kilometers, so very small. At the gauge, the Royal Botanic Garden of Edinburgh recorded a total daily rainfall of 57.6 millimeters. That was about 80% of the July monthly mean. So that suggests that the radar is probably underestimating the total rain. The radar rain estimate is about 35 millimeters for the Botanic Garden over the whole period. But all this points to the event is about kilometer scale in space and about 15-minute scale in time. So truly a cloudburst, so a small scale, intense event. And that poses some problems for the analysis. But first of all, I'm going to talk about the impact. So what's the impact on Edinburgh Castle? So as part of the project, mostly Kate and Young-Hwa talked to people at the castle, and architects, work managers, senior guides had more than 20 years working experience at Historic Environment Scotland. And so they said, well, seen similar things before where the waterspout overflow has been running, but not such an extent with overtopped actual outlet drain in the corner of Crown Square. So what happened was the outlet drain, there was too much water going through it and the water backed up in the square. Remember, this is the highest point of the castle. Someone else said, I've never seen anything like this happen. I've never seen rain like this up here the whole time I've been here. So this is an unprecedented event, is probably around at least 1 in 10, 1 in 20 year event, given these people will have had 10 to 20 years experience working on the site. Here's a video, hopefully works. Yep. Showing, so this is the Crown Square, and it's taken by one of the people working there, and you can essentially see very heavy rain falling and piling up on the ground as it comes off the roofs. So to do the impact assessment, what we need to do is get asset data. Which elements of the buildings or buildings were impacted either directly or indirectly? We collected damage estimate via semi-structured interviews with key property staff. We collected this in about January and early February 2022, so about 6 months after the event had actually occurred. And then we attempted to make a survey of indirect impact, such as repair costs, disruption time, and economic loss. And we'd captured that during the interviews and presented it back to them. So I'm just going to summarize this impact. And so essentially we split it into damage and loss. So damage, green, would be business as usual, loss within regular maintenance costs. Minor for damage would be a little bit of cleaning. Loss so loss is extra cost, out of contracted hours, volunteer, small and urgency purchases, additional HR costs. Moderate, we needed some partial repair required, maybe there's some limited access. Loss, high opportunity costs, potential additional resources required. So for example, parts of the building, parts of the site might be closed. And then severe, major operation required, the whole site needed closure, building completely closed. Loss, impact on safety, major economic or monuments loss, or required major salvaging collections. So let's start. So the building outdoor fabrics, there was overflow of the gutter and roofs, which in our classification of yellow is minor. No, unlike the Botanic Gardens, there was no water inside from the roof, downpipes or gutters. Direct cost, there was none. There was a little bit of extra cleaning hours under safety, no injured staff or visitors, so not very much. Building indoor fabrics, the Mary rooms, that's in our purples, that's moderate, and main visitor toilet was flooded. I'll come a bit back to the Mary room in a bit. Indirect costs, because of high humidity, increased threat of mold due to humidity. We had the carpet needed replacement. There was extra cleaning and monitoring hours for staff. No real issues on safety. The drainage system, the drainage was overwhelmed. Water rose 15 centimetres at the southeast corner of Crown Square. The main visitors' toilet, which is down near the entrance to the castle, had 50 centimetres of water. That's getting close to dangerous. Some water with debris at the exercise yard. No real direct costs, some more cleaning required from staff in terms of loss. Plant room, so a little bit of water came in, but no real issues. Gas meters were slightly damaged, more extra cleaning. So the collections in the Mary room are priceless in the sense they're not replaceable. So there was no damage to the collections. Indirect, there was no molds, developments, no reputational risks. Loss, there was 2 dehumidifiers needed to be bring in. Staff time, essentially handled by staff volunteering, 1 to 2 weeks of intensive monitoring, inspections and coordinations over the 6 months. About the pavements, well, cobble infills were washed away. That's fairly minor. Bit of pavement infilling, some contractor hours to fill this. The site, it was closed early. It was closed at 4 o'clock. Worth remembering that 4th of July 2021 is a Sunday during COVID, so there was only limited visitors, no significant impact on ticket sales, no refund costs. So in summary, overall fairly small, I would say. Edinburgh Castle is an extremely well-staffed site, though, unlike many other of the HES, Historic Environment Scotland sites. Staff live nearby, staff could get there quickly. Cleanup relied on additional voluntary work from staff. And I think, yeah, we were lucky because the paintings weren't damaged, one said. It was lucky the incident happened near to the closing time of day. And since the COVID pandemic, footfalls decreased to 1/3. So we have many less visitors. It was near the end of the day. So I think we classify that as a near miss. Okay, so now I'm going to talk about how we might calculate the change in probability. Now, the problem is what we originally wanted to do was use the UK runs a very high resolution model, 2 kilometer resolution or so, which has the big advantage that it explicitly resolves thunderstorms. However, and just estimate things from this. However, we weren't able to do this. So what we did was we focused on seasonal RX 15 min. So that's the maximum 15-minute rain in June, July, August, taken from radar data. So we have about 15 years of data. What we'd really like to do is fit a generalized extreme value, so that's our probability distribution, to this data. And from that, we can infer the event probability. But we have a very short record. So we hoped, or I hoped, we could trade space for time. So by pulling spatial extremes across time, we have a large sample. We could then estimate the distribution. However, these extremes are likely quite correlated. So in a 100 by 100 kilometer region centered on Edinburgh, pull together all the RX 15 min below 200 meters on land. I'm not going to show this because I don't have time, but essentially the characteristics of extremes look to be broadly consistent if they're on land and below 200 meters. So we're avoiding that ridge around the force, essentially. They occurred in the same 12-hour period, 0 to 1200 or 1200 to 2355. So that's essentially trying to escape storms, saying they're different, essentially, they're in those slots. Require events to be a bit larger than 25 kilometers in size. That's roughly what occurred. And when we do that, we get 300 events in the 2005-21 radar data. Within each of those events, we then take the 95th percentile quintile. So we have, say, a 100-kilometer area of extremes that occurred in the same 12-hour period. We find the 95th percentile in that. We consider that a regional extreme. I'll show briefly how sensitive the results are to the choice of that. I will confess this is fairly ad hoc. And I'll say at the end, maybe how could we do it a bit better? So, 2 things I'm going to focus on generally. I'm going to talk about July 2021, that's in general the red, and August 2020. So there was another extreme event in August 2020. The dashed line is the solid line is the actual extreme rainfall at the castle. This is fitting all the data. The grey bars are this is our best estimate distribution fit to this. The grey bars are the uncertainty. So what would you conclude from this? Well, empirically, if you looked at all the data and just pulled it and said, well, what are the odds of getting this kind of rainfall? It's about a 1 in a 100-year event. The regional extreme, which is for the castle quite close to the actual event that occurred, that's the actual rain, that's the regional extreme, is about 1 in 30-year event. We're saying that it's a regional extreme greater than 95, so then we say at the castle this is about a 1 in 500-year event. Point from that, estimating return periods is really quite difficult. We have limited data. We don't really understand the spatial correlation structure. So being cautious, we'll say this is somewhere between a 1 in a 100-year to a 1 in a 1,000-year event, given the radar data. Okay. What we'd actually like to do, however, is ask how has the risk intensity, so has the probability of this event changed? How has the intensity of this event change due to climate change? And so we're very fortunate in the UK that the Met Office, as part of its climate impacts program, has run what's called a convective permitting model, so CPM. And from that CPM, we can see how extreme rainfall changes on 1-hour timescales. So we could ask, how is the maximum seasonal rainfall, maximum hourly seasonal rainfall changing with climate change? That, of course, then begs the question, what do we mean by with climate change? So we did this by fitting a covariate dependent generalized extreme value and to data from the simulations, fixing. So the generalized extreme value distribution has three parameters. The shape essentially tells us whether it's fat-tailed or not. The location parameter essentially proportion roughly the magnitude of the average seasonal extreme event, and the scale parameter, which is essentially the width of the distribution. So if we have a location and scale that increases, then that will mean in this context that the extreme events will become larger. So we explored three different covariates from the model world. The central England temperature, chosen because we know we have a nice long record of central England temperature that's up to date, goes back a long way, has high quality. Sadly, we do have a Scottish record, but it isn't maintained, so it doesn't go up to date. Local temperatures, that is the temperatures in the Edinburgh region, and then more physically, the local saturated humidity. We'd expect extreme rainfall to be related to the maximum amount of humidity, the maximum amount of water that can be held. But when we look at this, we can work out the fit quality, and they're all roughly the same. So we chose to use CET because Ed Hawkins had already related that to global average temperature, and we'll see why we want that. It's observed, it has a long record, it's high quality. We don't really have a local temperature record of that's been homogenized, that's of high quality, that doesn't contain lots of sort of observing noise to be corrected for, and we'd have had to calculate local saturated humidity from local temperature. So we decided to pick central England temperature for that reason. So this shows the sensitivity, and I'm expressing it as a percentage. So each of these dots corresponds to a fit from 11 or 12 convective permitting models run with different boundary conditions at different temperatures. And this is showing the change on the x-axis, the percentage change in location parameter. So that's sort of the magnitude of the distribution. So the mean, it's a reasonable proxy for the mean with respect to temperature. So let's pick a point here. So for example, this point, and the colors correspond to that altitude. So the dark blues are over C. So we'll pick this point here over C. So for this point, the location parameter changes by about 4.5% per Kelvin or per degree of centigrade of warming. And then the other parameter we worry about is the scale, which is the width of the distribution. So a bigger scale is a wider distribution, which means that extreme events become more common if the distribution gets wider. And for this point here, that's about 8%. Now, we have some theory that tells us that we expect extreme rainfall to change at a rate that's around Clausius-Clapeyron, so that in a world that's wetter, we'd expect it to, the idea is that the extreme rain is when the entire water column precipitates out. And so we would expect that that's what these dashed lines are here. So in this case, most of these points are to the right of this dashed line, which is a little bit above 6%, which is what we'd expect from Clausius-Clapeyron. So that says the location parameter is increasing less rapidly than Clausius-Clapeyron, which is our theoretical expectation. Well, points that are above this dashed line here, the horizontal dashed line, are saying that the scale parameter, so the width of the distribution, is increasing faster than Clausius-Clapeyron. Okay, so some points about the colors. You can see here the yellows and browns are up in the top corner. That's why we restrict to below 200 meters. There's lots of blues here on the sort of top end of the scale parameter, where the model is predicting quite rapid rises. This red dot here is the mean, the average over all the points within 200 kilometers of Edinburgh that are above zero, so they're land, and below 200 meters, and that's our expectation for Edinburgh. So it's going to increase by about 5.5% per Kelvin of warming, and with the location, and about 10% in the scale. So a bit less in Clausius Clapeyron in the location, but quite a lot more in the scale. And then I'm going to go and talk about what the implications are. So we're going to use the observed central England temperature to define the temperatures to date. We've estimated from the radar data the distribution of regional extreme rains. That's what we're reasoning about. So we essentially can do for given any moderately long-term average central England temperature, we can ask what's the distribution given all these assumptions. So that's the basic idea. So we do this for plus 2K. So we want to know in a world that's 2K warmer, which if you ask me, I'd say we might meet. I'm not super optimistic, but we might meet. Then we can use the relationship between central England temperature and global mean temperature to predict what central England is at plus 2K. And then use that to say what the distribution of extreme rainfall looks like, and then use that information to infer all kinds of things. We calculated pre-industrial, which is the late 19th century, having now been defined by the IPCC, 1850 to 1899. The 1980s, when I was a student, both an undergraduate and a PhD student in Edinburgh, as a way of kind of thinking about change over lifetime. Today, which is essentially the last decade, and then a warmer plus 2K. And then both risks and intensity are expressed relative to pre-industrial. So all that's theory. Let's see how it turns out in practice. So first of all, let's talk about the percentage changes in intensity and probability ratio. So the Edinburgh regional one, that is this solid line here. The dashed line here is the 2021, is the 2020 event, which actually had a larger scale, more extreme rainfall, not over the castle, but over bits of Fife. And actually probably caused a real derailment at Stonehaven. So this is the change in intensity. The dashed lines here are showing what Clausius Clapeyron would give you, just so we can see if it's more or less in Clausius Clapeyron. And then the axis is return period on the bottom, so 20, 40, 60, 80, 100. This is the 2021 event. This is the 2020. And then on the top is what the radar RX15 min, so the RX15 min rainfall in millimeters per hour. So what the maximum 15-minute rainfall in a summer would be and what the distribution is. Essentially what that says, so here's the 1980s when there's basically an increase in intensity, which is fairly flat over periods from 20 years up of about 2%. So back when I were a student, which to me is, well, possibly quite a long time ago, coming up to 40 years now, there wasn't a great deal of change in rainfall intensity in terms of different return periods from the pre-industrial. In the past decade, 2011 to 2021, we're seeing changes maybe about 8%, and that's well above the Clausius Clapeyron. We've had about a warming of a bit under, I think it's about 0.8 degrees since the late 19th century. And then as we go to the plus 2K world, which I think we reach about 2050, we're talking 16, 17%, though with fairly large uncertainties. And then this plot here is showing the probability ratio. So we ask for a given rainfall amount, for a given RX15 min, how much has climate change increased the probability of that? What's the ratio between that and the pre-industrial? So again, broadly, it's not so flat as the intensity. It tends to increase with time. The uncertainties get larger. So in the 1980s, when I was a student, we're talking about maybe 5 to 10%. Now we're talking about 20 to 40 or 30 to 45 to 50%, depending on what we look at. And then when we hit the 2050s, when we think we've reached a plus 2K world, we're talking for the event that occurred somewhere between 60 and 90% increase in risk. So the event is 1.6 to 1.9 times more likely than it is in the pre-industrial world. That's actually the main findings. Then we kind of look, remember there's a rather empirical one, we chose quantile within a region of extreme event that happened at the same time. And in a sense, the story here is a somewhat increase in intensity with time. Here's the return periods to the different events. So if we'd chosen the 10%, the event would have been like a 12-year event, 1 in 12-year event. Here's the probability ratios, which are much less sensitive to changing for the actual event we saw. So that's some sensitivity in terms of intensity to exactly how we define the event, less so for the probabilities once we're above the 80% or so. So I'm going to summarize. So 4th of July, 2021, a short duration, small scale, high intensity rainfall, a cloudburst event impacted Edinburgh. We carried out a rapid impact study to see what the impact was. So we did that 6 months later. Generally small, though the damage to rooms that hold irreplaceable art collections took 6 months to repair. During COVID and near closing time, so a small number of visitors. So if it occurred, let's say, a couple of hours earlier, it could have been quite different in terms of impact on visitors. If it wasn't for COVID, there would have been many more people. Edinburgh Castle is a very well-resourced site. There are lots of people that work on the castle. A lot of the rest of Historic Environment Scotland sites are much less resourced, don't have people living near them, they're in rural areas. And we also carried out an attribution study. So we find that intensity is increasing in the convective permitting model, which is what drives the results by the Clausius-Clapeyron's, what our theory says, plus 50%. Changes in risk today for similar events relative to pre-industrial of about 30%. Small changes in the 1980s. So over a 30-year period, going from the 1980s to the 2010s, there's been, I would say, a very substantial increase in risk. Most of the risk changes occurred since then. So any building codes and things about precipitation that are built around the idea that we were in that world are now quite likely wrong. And we expect big risk increases of such events by 70 to 80% at a plus 2K warming. What adaptation could be done? Well, Historic Environment Scotland should make more use of nowcast from rainfall radar. An hour warning would make a difference. It would allow preparation, moving visitors around. Though I think to make it work, it likely requires some work at the Met Office end, essentially to get this information distributed to sites that may have 1 or 2 people working on them, are far from being an expert in meteorology. And so it's going beyond the sort of current practice of essentially yellow, amber, red warnings, but actually allowing some way of getting nowcasting to people who can make decisions. Improve the drainage of the castle. Apparently that is still being thought about. The event was probably in the end a near miss. COVID, as I said many times, meant much reduced number of visitors to the castle and the environs, which made it a lot easier to deal with. So some other thoughts, should you believe what I found? Well, radar rainfall data is not in situ precipitation data. It has biases, and I tried to say what those might be, but they're quite hard to estimate. Rainfall radar is not homogeneous. The way that the radar has been processed to produce a precipitation estimate has changed with time. Grouping to give independent data, which is one of the challenges of research and which was needed to do this distributional fit, is fairly ad hoc. I think there are better ways. I have a PhD project advertised. Hopefully I'll have a student to work on it. The convective permitting model has lots of biases. It's probably warming much too fast due to the driving model. We didn't have time to assess the model at all, this CPM. Is it getting the summertime extreme precipitation for the right reasons? Is its sensitivity plausible? Is its predictions about Clausius-Clapeyron plus 50% reasonable? Is it reasonable to apply sensitivity from hourly mean seasonal max convective permitting data to 15-minute regional extremes? And if you want to see more, there's a report available from the National Centre for Resilience at GLA.Glasgow, so click there, or you can actually get the report directly from here. And we have a paper that's under review, which deals with some of the issues in the Bulletin of the American Met SOC, which I hope will be out fairly soon. And I think that's me. Brilliant.
Okay, Simon, thank you very much. That was quite fascinating. One question I'd like to ask, which is really your last part there, where you're saying that you know, radar data is not in situ precipitation data, but did you actually get a chance to compare the radar data with the physical data from the weather station at the Botanic Gardens? Was any cross-referencing at all?
Only very crudely, so only on the day itself. We didn't really have time to go and get hold of high quality hourly or sub-daily rainfall network and compare it. I mean, in its defense, we have anchored everything in what the radar was saying. So we're essentially saying the radar said this was a 1 in N year event with an intensity of, so what, of, well, I can't quite remember, about 90 millimeters per hour, I think. So we're self-consistent, but I worry that the rainfall data might actually have some odd biases, which are because it's not homogeneous.
Yeah. And did anyone look at the same time at, say, for example, the waters of Leith, looking at the actual impact on, you know, you were saying the castle was great because it had absolutely no impact from a water course at all.
Yeah.
But did this event have an impact on the water courses?
It did. There was actually quite a lot of flooding across Edinburgh. We originally tried to persuade NERC to fund it as an urgency grant. They said it wasn't in their remit. So there was quite a lot of flooding in places like in the Princess Street Gardens and in the shops off Princess Street in their basements. The water of Leith broke its banks, as I think it tends to. And so there was some sort of flooding down at the bottom. But actually the biggest impact was in the Botanic Gardens, where their 1960s building had a flat roof, and the pipe that was draining the flat roof runs through the center of the building, and the pipe broke, which is where we first heard about it. But we focused on the castle because Historic Environment Scotland were co-funding the work, and that was a natural focus. They wanted to know, and in some ways doing a rapid impact assessment on a unique building like that has lots of sort of is quite or a complex like that, I think has likely to have more impact in the longer run.
Yeah. Knowing HES, it's something that in my own profession people will deal with quite a lot. To them, the difference between 1 in 100 and 1 in 1,000 is a huge variation. How seriously are they taking this piece of research and implementing any recommendations?
That's a good question. Well, the problem is the person who we were working with to do the work has left them and got onto National Rail. I think this is a general challenge actually for climate change adaptation. So this work shows that I think that it was a near miss, and that such events are becoming more common. And I think the details of the event aren't too important, because you can see from the sort of maps I showed, the plots I showed, but let's go the wrong way. The intensity increases are fairly flat, but of course the risk of breaking key thresholds is increasing. So I think it's a general issue for adaptation that you need to be prepared for a climate that's getting, say, more extreme in particular ways. But actually, particularly in the public sector right now, I think finding resource to invest. So as I said, a few things would be better now. I think the Met Office is a nowcasting system. It's just that people don't know how to use it, or sorry, don't know how to make decisions based on what they see. So there's a need for a little bit of what I call practical Met training. And there's some nice work on artificial intelligence, which is doing nowcasting for radar rainfall. So I think a little bit of preparation, and then a bit of capital, probably quite a lot of capital spend improving the drainage. But I think finding the resource to do those things in the public sector, and HES is in the public sector, is very hard at the moment.
Yeah, indeed.
What's the word? Penny wise, pound foolish.
Is that one way of putting it? Right, there's a question from Fiona McClay. Did you look at how your return period estimate compared to the FEH DDF model, brackets, which admittedly I don't think goes below 1 hour?
No, and thanks, Fiona. That's a really good question. I don't know FES flood. Could you explain FEH DDS? I think I didn't even know that such a model existed, but probably I should. I mean, I think I'm going to guess, but Fiona can probably correct me quite, that this is going to be based on in situ radar rainfall stations with hourly data. I don't know, is the honest answer. I think the part of the problem is I couldn't get hold of data from the botanics for an hour rainfall to say what it was. So I don't know. I mean, I was very cautious on the return period because of the problems with autocorrelation. So one estimate was 1 in 100 years, and the other one 1 in 500 years. And so I basically stuck my finger in the air and went, well, it's probably somewhere between 1 in 100 and 1 in 1,000, which perhaps it shows how difficult it is to estimate return periods.
Okay, I don't know, Fiona, whether you want to follow up on, as Simon was saying, regarding the FEH DDF, but a question from Roy Thompson.
Fiona did say that.
Right. Jim Hansen's latest paper is putting further global warming at 10 degrees, brackets, well above your hoped 2 degrees C. Does Calces Clapeyron continue to scale similarly to such extreme temperature increases?
Oh, that's a good question, right? I suspect if we reach 10 degrees, I don't think we'll be worried. I think we might have a whole host of other worries as well as extreme precipitation, and any hope of adaptation is doomed at that level, as I suspect is lots of things. The convective permitting model actually is run within a climate model that has very high climate sensitivity. So I think the temperatures get up by 6 or 7 degrees above current. So, and the relationship was estimated over the whole thing. So it does seem to behave quite linearly up to that level. So I think for 6 to 7 degrees, but global warming at 10 degrees, I don't know. As I said, I suspect we'd have many worries, not just changes in extreme rainfall at that kind of level of warming.
Okay, thanks for your follow-up, Fiona, to clarifies it. Thank you. Okay, don't see any other questions. So just Simon, thank you very much for your talk tonight. Very interesting, actually. It's a fascinating subject, and you know, like most weather meteorological talks these days, it's impacted by global warming, and it's going to be with us for a long time yet, and a lot of discussion is going to happen yet. So research like this is quite vital, I feel, to what's going to happen in the future and how we're going to look at things. You know, especially when it comes to buildings like this, you know, how we're going to deal with it, how we're going to deal with increased events, you know, coming from 1 to 1,000 to 1 to 100 years, and probably even less in the future. So quite fascinating. Thank you very much. I would just like to thank you personally on behalf of the Scottish Centre for your talk tonight, and I would hope that everyone there would be applauding and thanking you again. We'll look forward to seeing everyone at next month's talk. And I would like to just thank Hayley, Alan and Richard for behind-the-scenes organisation for tonight. A few comments coming in from people just thanking you, Simon, just for your very thoughtful and educational talk tonight. So thank you everyone, and I would wish you a very good evening, and Hope that the weather wherever you are is exactly what you wish for, and we look forward to seeing you at our next talk next month. So thank you very much, everyone.